All right, I'd like to discuss this Ampere's law problem. I like this problem. It's highly conceptual and kind of fun to think about in terms of fields. So let me introduce the problem. We're looking end on here at a long circular pipe on the right, and the pipe's hollow in the middle there, and then there's current going into the page as shown. And the current is evenly distributed in the pipe. So imagine it's like some metal pipe of some thickness, as you can see there, and current's traveling through that pipe. And then to the left of the pipe, we're looking end on at a wire there. Okay. Now there's also current in the wire, but we don't know anything about that current. Notice that the current in the pipe is given as I, and the direction is given too. And then there's spacing and stuff that's given to us here. Point P in the diagram is just a point in space there, and we need it for the problem. So, okay, give yourself a little bit of time to interpret what this question's asking. So what it's asking for us to determine here is the magnitude and direction of, and this should be a D, of the current in the wire such that the net B field at point P is equal and opposite to the B field at the center of the pipe. So there's a lot going on there, but the focus here is that this last part here, let me highlight. Net B field at P is equal and opposite to the B field at the center of the pipe. And what I want to do is call that B field at the center of the pipe. Let's just call that point C. So we have some reference point there. Okay. So what this constraint here means is that the B field at P is equal and opposite to the B field at C. All right. So in a problem like this, where you're given a bunch of conceptual relationships, one of your first moves should be like, how can I write those relationships in more of an algebraic manner? And sometimes it takes a couple steps to do that, and that's fine. In this case, the equal and opposite nature of the question means I need to be thinking about this as a vector. And their magnitudes are the same, but it's important. The directions are really important. The equal and opposite part is important. So I'll focus on that too. That matters. All right. So yeah, let's think about then a place to start with this is what can we possibly know about the B field at the center of the pipe, right? If we need P to be equal and opposite to the center of the pipe, can we figure out anything about the field at the center of the pipe? And I would encourage you to think about the pipe itself and how or if the current in the pipe will have any effect on point C there inside the pipe. So if you think about that, you can kind of imagine this idea of, let me change colors here, that the B field, remember that the B field due to a long straight wire is just concentric circles around that wire, right? So if I, actually, I'm going to not draw right on the pipe itself, but I'm going to say, okay, here is point C, and the pipe is around that point, right? Then I can consider that there are going to be all these different concentric, these are just the B field circles. Let's see, this is going into the page. So the B field is going to be in this direction. So this is B that I'm depicting here. And I'm going to have different circles that look all the way around, but that are all going to go through. What we're interested in is where the B field lines are actually going to go through point C. And they're all going to be clockwise because these currents are all going into the page. All right. So that's one way of kind of thinking about this. And you can think about like there would be a gazillion of these little circles, right? As they all add up now at C. So if you look at that point C then, and I say like, all right, I'm just going to, what if I just look at point C right there in the middle? I can see that what I'm going to have is I'm going to have, let's see, maybe I should number these to make this more clear. I can number them like 1, 2, 3, and 4. Just looking at these 4 contributions and knowing that everything else would contribute with the same symmetry. That's what I'm trying to get at there. So the contribution at C due to 1, there. So look at B field 1, that's a clockwise circle. At C, that's going to the left. The contribution due to 2 at the point of C, that's going upwards, right? The contribution at C of 3, that's going to the right. And the contribution of 4 at C, so again, clockwise, at point C, 4 is going downward. So these all are actually going to sum to 0. So this is kind of a physical explanation. There are a lot of different ways you can look at this, but this one I think is fairly simple, and I like how physical it is, that the pipe doesn't contribute at point C. I'm going to say that again. The pipe itself doesn't contribute at point C. So what that means is that the only B field that's at point C there is the B field that's due to the wire. So I can say BP, whoops, I didn't mean to say that. BC is what I mean to say here, is due to wire only. Okay, so we can figure that out, that at point C, due to the symmetry, the pipe doesn't contribute. The pipe doesn't contribute inside there. Only the wire would contribute. Great. So now let's think about point P, because at point P, they'll both contribute. So consider point P for just a second. Now let's think about first, because we have the direction of current of the pipe, let's think about how that's going to contribute at point P. So if we use right-hand rule, we see again, we have clockwise circle due to our current going into the page. So at point P, the B field due to the pipe, there is going to be upward. So I'm going to call this B. Let's see, I'm using BC for over here. I'll call this BP here. And that's due to the pipe upward at point P. All right, so now we have to throw some logic at this and say that, remember, this problem is asking us for the net B field to be equal and opposite at P and C, right? Equal and opposite at P and C. So how do I know what the direction of current in the wire is going to be? And one of the ways that you can pause the video right now if you haven't spent time thinking about this yet and figure it out. It's kind of a fun puzzle. But one of the things that I can think about is that point P is, one thing that's for sure here, point P is closer to the wire than point C, right? So I know that the B field contribution from the wire is going to be larger at P than it is at C. So I could say something like, I don't know, notation wise, I could say like B of the wire, BP of the wire, just due to the wire, is greater than B is C due to the wire. It's only due to the wire, but still, just for notation, I can put that in there. Because I know that the B field's going to fall off as it goes with 1 over R, right? As I got farther from the wire. So why is this important? This is important because if we need these two to be equal and opposite, there's no way that, let me choose this case and I can maybe show you by exclusion. If we had say we used the case where the current in the wire was coming out of the page. Say we used out of the page. If we used out of the page for that current, that would mean that the B field due to the wire is here, right? Would be upward. This is B due to the wire. And that here, this B field would have to be less than that because we're farther away, but it's also upward. So this would be B due to the wire, right? Now, this is not going to give me an equal and opposite situation. The overall B field at point P is going to be way, way larger in magnitude. It's going to be in the same direction. So going through this shows us there's no way we can meet the constraint that we're given with the wire being out of the board. So I'm just going to back this up and say what we just figured out is that this wire current needs to be into the page. If the current in the wire is into the page, what that can give us there is it can give us, we know then that to the right of the wire, it's going to be all downward, right? So this can be here. That's like my B at P, or sorry, B sub C. That's all due to the wire, remember. That's 100% due to the wire. And I know that the B field at P has to be equal and opposite to that. So this is going to be a little bit closer in. It's going to be a little bit larger. Hopefully I'll draw this kind of okay here. And this is the B field due to the wire, right here. Or I guess that's different notation than I used before. B field at P due to the wire. So if I sum up, let me use a third color. If I sum up the two arrows at point P, what their sum gives me would give me something like this. That would be the overall B at P. So what I could do is I'm going to change notation here. B P due to the pipe is upward. B of P due to the wire is downward. So the overall B of P is upward. And then what I'm looking for, of course, is I'm looking for equal and opposite, this here and this here, equal and opposite. I was just freehanding those, so they didn't turn out exactly right, but you get my drift here. We can figure out all the particulars analytically. But I love the concept here because you can go through, you can figure this much out just by looking at the situation and thinking about the fields and applying logic. Okay, so now that we have that figured out, we can do the Amperian loop stuff, right? So what I'm going to do here is just say that we know that the B field, let me change my color. The B field due to a long straight wire, and you can derive this using Biot-Savart, you can derive it using Ampere, but long straight wire, we have mu naught I over 2 pi r, and I'm going to use that result. If this were an exam situation, I would want a student to derive that using either Biot-Savart or Ampere, but right now I'm going to say, okay, so pretend we've done that derivation and we have long straight wire. Then I know that I can figure out what these different B magnitudes are using long straight wire here. And I can apply long straight wire to the pipe as long as I'm outside the pipe. So if you recall shell theorem when we were looking at charged stuff, this current carrying pipe is a little bit similar to that, where it doesn't contribute inside the pipe, but once you're outside the pipe acts as if all the current were concentrated at its geometric center. That's due to the perfect symmetry of that situation. So then we can just kind of start calculating this stuff out here. So then I have that B, I can start adding my stuff up. Let's see, let's do it this way. So B at P due to the wire, I can start figuring that out. Mu naught I wire, I'll call I sub W I wire. That's the thing we're actually trying to find, right? Over 2 pi big R. B at P due to the pipe. I'm just figuring out magnitudes here, right? That's mu naught I is given as the current in the pipe. And now we have to go as our distance from the geometric center, so center to center distance. So that's going to be 2 pi times 2R there. And then the last one to figure out is B at point C, which is due to the wire, totally to the wire, right? And that is mu naught I wire over, and there we're a distance 3R, 2 pi times 3R. And then we can set up our algebraic situations there. So if I know that magnitude-wise, the magnitude of B at point P equals the magnitude at point C. And I know I've gotten the directions opposite already by figuring out the direction of current in the wire. So I can kind of just play with magnitudes here. So I know that when I sum everything at P, so I'll write this out in general first, BP wire plus BP pipe is going to be equal to BC due to the wire. All magnitudes. Okay, so you could figure that out algebraically and solve for, so you'd sum those three, solve for I wire, and your result there will be that I wire equals 3/8 of that given I, the I that's inside the pipe. Oh, and it is in the same direction. So also into the page.